So let's continue on. Now we're moving into the periodic table section. And actually, I'm going to go back up to the electron configurations. I don't have tons of stuff on here, but if you know this, you know a lot about electron arrangements. So we're going to look at the element arsenic. Arsenic has 33 electrons. You can see the number right there on the periodic table, 33. Or if I pull up this periodic table, this might take a minute to load. There we go. So arsenic is right here, and you can see the 33 perhaps better. So this number tells us the number of protons, but if there's no charge in the atom, it also tells us the number of electrons, and we just talked about that. So let's pull this out and go back to zoom. All right, so 33 electrons is what we're dealing with. So let's go ahead and put them in. You know, they go from low energy to high energy, so you'd have an up and a down. Remember, on the answer key here, instead of doing an up and down arrow, I put in a 2 right there, but it means the same as an up and down. Same thing here, up and down, up and down. But notice I put them in, since I have the liberty of showing you, I'm putting them in single, 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 then pair, 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 because they go into one at a time until they pair up, until there's one in each orbital, then they have to pair up. Then they start the next one and they pair up because there's only one bed in that sunny room. Now we're in the pink room. They go into bed one at a time, then sunny room on the 4th floor. Then we go to the dark room on the 3rd floor. And now we're up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. But I'm going to 33, so I have 3 more to put in. 1, 2, 3. All right, so that's the arrow diagram. The electron configuration. Now, on the final, I may make this in a Google form, and so I may have questions like, how many electrons would you expect to see in the highest energy level of arsenic, for example, and then you'd have 1, 2, 3, 4, 5, something like that. So you may not actually be doing the arrows. I haven't made it up yet. I got to think about how I'm going to frame that question. Okay, so full electron configuration, we know then the first energy level, the S sublevel, the 1s, there are 2 electrons. In the 2s, there are 2 electrons. In the 2p, 2, 4, 6 electrons. In the 3s, there are 2. And in the 3p, there are 6. And in the 4s, there are 2. In the 3d, there are 10. And in the 4p, there are only 3. All right, so that's your complete electron configuration. The outer shell configuration only includes the outer shell. So the outer shell is the highest energy level. Don't miss this. It's always a struggle to get people to remember that the outer shell can include the S and the P. It will never include the D because the D always has a higher S in front of it. Okay, so in this case, the outer shell configuration would be 4s2 and 4p3, like that. The noble gas configuration uses the noble gas from the previous row. So if we're going to look back at a periodic table, bring one back in here. So here's arsenic right here. The noble gas on the previous row is argon, and argon has 18 electrons. So what that means is that 18 of the electrons that are in this configuration here can just be written like this, AR, and that covers 18 electrons. In other words, it covers all of this. So the stuff in these brackets here and that mean the same thing. So what's left over is 4s2, 3d10, 4p3. So that would be the noble gas configuration for arsenic. All right. So if I gave you this symbol, just a little extra bonus since you're watching this video, if I said this Kr, and I'm going to look at a periodic table here. So Kr 5s2 4d2. What element would I be talking about? Well, then you look at your periodic table. And Kr is right here. So I know that whatever element I'm talking about has 36 electrons. Then you go to the next row down, 5s2, 4d2. So the element I'd be talking about would be zirconium, Zr. So that's how you could use noble gas configuration. To avoid writing all the complete electron configuration, you can use a noble gas as a shortcut. So that would be zirconium. All right, now moving to the periodic trend section. I took the liberty of drawing a nice high-quality artistic rendering of the periodic table here. And I want to remind you that as you go to the right, atoms get smaller. And as you go up, atoms get smaller. So there's a general trend in this of this type. As you move up and to the right, atoms get smaller. And as you go down and to the left, atoms get bigger. Okay, so now which could be an atom of fluorine? So if you look at a periodic table, here's chlorine, here's fluorine. So would fluorine be bigger or smaller? Well, fluorine's further up, so fluorine would be smaller than chlorine, so the atom of fluorine would have to be letter B. Which could be an atom of bromine? Well, let's see, chlorine is here, bromine's here, so bromine's further down, so bromine would be bigger. So the bromine would be D, that's bigger. The highest ionization energy, that would be the atom that holds its electrons the tightest. So another way to say this would be most energy needed to remove an electron or to pull off an electron. So that would be the smallest one, wouldn't it? Because they're small because they're holding their electrons tighter. So that'd be letter B, which might be a chloride ion. Notice that there's a little minus sign right there. So if it gains an electron, would it get bigger in size or smaller in size? And I'm thinking it's kind of logical that if you add an electron, it's going to get bigger, so that would be circle D. The furthest right in the series on the periodic table. So if these were all in the same series, which one's furthest to the right? It would be the smallest one, because the atoms get smaller as you go to the right. Which would be closest to the bottom of a family on the periodic table. As you go down and to the left, things get bigger. So which one's closest to the bottom would be the biggest one. And the one that's most likely to lose an electron, this number 56, would be the one that's not holding its electrons very tightly. So that would be the bigger one, because if they're big because they're not holding on to their electrons super tightly. And then we already answered this question, the largest atoms are in the lower left. Which one's the largest atom? Here, you got lithium, boron, carbon, and neon. Here's where they are. Here's lithium, here's boron, carbon, and neon. So the biggest one's the one furthest to the left. That'd be lithium. These are these general trends you ought to be writing on your little cheat sheet. Which is the smallest atom? Well, you got lithium, sodium, potassium, and cesium. They're all in the same family. So they get bigger as you go down. We want to know the smallest one, so that's one furthest up. It's lithium. Which is the most reactive? Now these guys are metals. They react by losing electrons. Remember their charges are positive when we're writing formulas? Nonmetals react by gaining electrons. So the most reactive metal, that'd be the big ones would lose easier. So you want the biggest one is the most reactive as a metal. So cesium was the one furthest down, that would be the biggest one. So that's D. The most active nonmetal, since nonmetals react by gaining electrons, small atoms would gain electrons easier because they're pulling in electrons anyway. So these are sulfur, here's sulfur, carbon, fluorine, iodine. Fluorine is the smallest of those, so that would be D. Okay, now we're going to write some formulas. Copper 2 sulfide, you have to go to your periodic table and find copper, and it's copper Cu. I'm probably going to use the strange names table on the final, so just be prepared for that. Then sulfur, copper's +2 because it says copper 2 here. If you look at copper, it can either be 2 or 1. Let me pull that down on the other table. Okay, so here's copper. This shows up a little better. See, it's got a +2 and a +1. There are lots of elements that have these multiple charges. So if there is more than one possible charge, I'll always tell you what charge to use. So this is copper with a +2 charge because it says copper 2. Sulfide is -2. So if you click over here, go look at sulfur, it's right there, it's -2. So since 2 is equal to 2, the final answer is just CuS. You don't need to put the charges on, but you do have to think about the charges. The next one's potassium phosphide. So if you look at potassium, over here, potassium's got a +1 charge right there. Phosphide, remember the IDE ending means plain element, that's -3, so you're going to have K3P. Next one's chromium 2 phosphide. So if it's chromium 2, you know chromium's got a +2 charge, and phosphide we just looked up as -3. So now we got to have a common multiple of 2 and 3, so that'd be 6. So you multiply 2 times 3 to get 6, you multiply 3 times 2 to get 6, so our final answer is Cr3P2. Barium oxide is barium, oxide like this. You look at your periodic table, barium you'll find is +2, oxygen's -2, so it's just BaO. Nickel 3 iodide. Okay, let's take a look at the periodic table. Iodine might be a little confusing because see, it's got all these different charges listed and I didn't tell you which one. But if we're looking at nickel combined with iodine, nickel's over here. Which is more electronegative, nickel or iodine? So iodine attracts electrons more because it's way farther to the right. It's further down too, which make it attract less, but looks like it's further to the right is more relevant than up and down because it's so much further to the right, but it's only one row down. So we would say that iodine is more electronegative than nickel, and if that's the case, then iodine would gain electrons, and if that's the case, the only possible charge is the -1. Because iodine is more electronegative, it takes the electronegative, it takes the electrons from the nickel, so it's -1. So if the iodine's -1 and the nickel's +3, then you're going to have 3 -1s to match the nickel. Okay, here's a big number one. So you got 10. 10 is Sn. This number is a 4, not a 5. Some people have been thinking that IV is a 5. Nitride is nitrogen. And if you look at nitrogen, it's up here. It's got a -3 charge. So now you need a common multiple of 4 and 3, which you may know is 12. So 4 goes into 12 3 times, so we put 3 there. 4 times 3 is 12. 3 goes into 12 4 times. So our final answer would be Sn3N4. Iron 2 hydroxide. Iron is +2 because that tells us that. Hydroxide is a polyatomic ion. You have to remember that that is a weird thing because normally IDE means a plain element, but hydroxide and cyanide are two that end in IDE that still are polyatomic ions. So hydroxide's OH with a -1 charge. Oops, I don't know what pole means. Okay, so the hydroxide to be OH has a -1 charge. Now since that's a 2 and that's a 1, I'm going to have 2 1s to match it. And since it's a polyatomic ion, it has to be in parentheses if there's more than one of them. So there are 2, so I had to put it in polyatomic ion and put it in parentheses. Lithium sulfide. Now you know. By now you should be figuring out how to find these charges. So I'm just going to put them up here. +1 -2. That's a 2. Barium phosphate. BaPO4. The ATE ending tells you that it is on the bottom of the periodic table. You can kind of see it right here. Remember, there's a dihydrogen phosphate, a hydrogen phosphate, and a plain phosphate. This is the plain phosphate. So it's got a -3 charge. Barium was +2, so you're going to have 3 bariums to make 6, and you have to have 2 phosphates to make 6. And since it is a polyatomic ion, and you need more than one of them, put the 2 out there. Copper 2 acetate, be copper +2, acetate C2H3O2. That's a -1. All right, so I'm going to have 2 of these, 1 of these. I'm going to have, I got a +2, I mean, here, and a -1, so I'm going to have 2 of these to match the +2. And since it's a polyatomic ion, you put it in parentheses. And now we get into the hardest things that we've done, probably. And this is just balancing equations. We have 4 of them to do. So I have, what you're going to do is write this symbol down. This is kind of like the precipitation lab that we did. You have aluminum chloride, yields, zinc and chloride. So I got the symbols written down. And now we're going to do the formulas. So that's a +3, and that's a -1, so that has to be a 3 down here. This is a +2, that's a -1, so that has to be a 2. So in case you're wondering, how do I know this? I went to the periodic table. So aluminum is +3, and chlorine's -1, and so on. There are no charges or subscript on these guys. They're really 0 because they're not combined with anything else. All right, so now the third step. Remember the 3 steps. We had combos, and then we had the formulas. I've already kind of given you the combos, so you just have to write the symbols down. And then balance it. To balance, you use coefficients. To write the formulas, you use charges and subscript. So what's uneven on both sides of the arrow? If you look at the equation, you see there's a 3 here and there's a 2 here. They're uneven. That's the only thing that's uneven. So you make them even by finding a common multiple of 3 and 2, and that's 6. So what could I multiply 2 by to get 6? Well, what would I multiply 3 by to get 6? So when I put the numbers in front, I change the number of aluminums also. Because what that 2 means is you've got 2 AlCl3. It's like this. So there's 2 of them. So there's 6 Cls, 3 here and 3 here. But there's also now 2 aluminums. And there's only 1 aluminum on this side, but you fix that by putting a 2 there. And the same thing is true of the zinc. The side effect of multiplying this by 3 was it made 3 zincs. So you got to come over here and put a 3. All right, and then the next one, aluminum nitrate, symbols, AlNO3, plus sodium hydroxide, Na with OH. Yields, the arrow, sodium nitrate, Na with NO3, and aluminum hydroxide, Al with OH. All right, so now I'm going to put the charges on. We get the formulas 3, -1. So that's going to have a 3 down here. This is +1, -1, so that formula is fine. +1, -1, so that one's fine. +3, -1, so you're going to have 3 of these OHs to match the +3 for the aluminum. That was step 2, formulas. Now balancing, what's uneven? Well, it looks to me like I've got 3 NO3s here, but there's only 1 NO3 over here, so I'll put a 3 in front. The side effect was it made 3 atoms of Na, so you come over here and put a 3 in to make 3 NAs. That has a side effect too. It makes 3 OHs, but over here you have 3 OHs, and so now you're finished. Okay, next one, aluminum and iodine, and it makes aluminum iodide. Didn't write that very well. Let's start that again. Aluminum iodide. All right, so those are the symbols. The formulas, iodine is one of a group of elements that I always call the Brinkelhoffs. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine that always occur in pairs when they're by themselves. See, iodine's not with anything else, so it always occurs in pairs when it is alone. So that's I2 instead of just I. In the classroom, there's a list of these elements that occur in pairs on the board in the front. Okay, then aluminum here, that's +3, and iodine's -1, so it would be AlI3. Okay, so there's our formula step. Remember the 3 steps, formulas. Third step is balanced using coefficients. So what's uneven? Oh, it's the i's. So how many i's are here? 3. How many is here? 2. Common multiple? 6. What do I multiply by? 2. What do I multiply by? Now the iodines are even, but by putting this 2 here, I made 2 aluminum, so I also have to put a 2 over there, and then we're finished. All right, last question. Calcium nitrate. You got calcium and nitrate. Looking up the symbols on the periodic table. Sodium and phosphate. Again, the ATE, remember, that means you look at the bottom. Yields sodium nitrate and calcium phosphate. There's my symbols. Now I'll do formulas. This is plus 2, that's minus 1, so I'm going to have parentheses and a 2. Plus 1 minus 3, so I need to have 3 sodiums. No parentheses, though, because this is not a polyatomic ion. Plus 1 minus 1, so that's fine. Plus 2 minus 3, not fine, got to fix it. Common multiple 6, so I'd have 3 of these and 2 of those, but they have to be in parentheses because it is a polyatomic ion. All right, so what's uneven? Well, I just start with the first thing. Sometimes in one like this, I think this is the most complicated formula, and I kind of work off of that. So there are 3 calciums. Over here there's only 1, so you put a 3. So that multiplies this whole formula by 3. So you have 3 calciums, but now you have 6 nitrates because 3 times 2 is 6. So I had to put a 6 over here. That made the 6 nitrates work. So you got nitrates times 6. But it made 6 sodiums. And over here there's 3. So what can I multiply by to get 6 sodiums? Put a 2 in. So 2 times 3 is 6. 6 times 1 is 6, or even. But then I'd also change my phosphates because there's 1 phosphate in the formula, but when I multiply it by 2, now I have 2 phosphates. But on this side, there are 2 phosphates. So that one is not complete. Once again, there are 3 steps on these: combinations, formulas, and balance. Likely that I will not have you write equations like this, but actually give you scenarios and ask you, like on this one, I might say, how many atoms of aluminum would you find in the balanced equation for the reaction of aluminum and iodine to make aluminum iodide? So you'd have to write the equation in order to answer the question about the aluminum. Kind of like I did on the strange names quiz we did on naming, where I asked you questions about the formula, but you couldn't answer the questions unless you wrote the formula. All right, that'll be that's my final review. Hopefully that helps.